1.2, Lesson 2, Rate of Change by Equation, Graph, or Table. Objective for today's lesson: given a table of values that shows that y is a function of x, you'll be able to estimate the instantaneous rate of change of y with respect to x. So we've been working with this vocabulary for the last 2 or 3 lessons. Average rate of change. Graphically, that's the slope of the secant line. And the instantaneous rate of change, when the 2 points on the secant line, when the second point on the secant line moves closer to the first point, the slopes of the secant line begin approaching a particular value, which would give us the slope of the tangent line, which would be the instantaneous rate of change. That is also called the derivative of y with respect to x. We're working with the same ideas. Yesterday, we looked at those ideas when the function was presented as a graph. Today, we're going to look at the same ideas when the function is represented by a table of values. So here we're looking at example 4, and example 4 reads, a mass is bouncing up and down on a spring hanging from the ceiling. And when we look at the figure, here's our ceiling. We have a spring here, and attached to this spring is this mass, and this mass is bouncing up and down. So the distance of the mass from the ceiling is increasing as the mass is going down, and the distance of the mass from the ceiling is decreasing as the mass is going back up. So its distance y in feet from the ceiling is measured by a calculator distance probe each 1/10 of a second, giving this table of values in which t is time in seconds. So here we have at 2/10 of a second, the distance of the mass from the ceiling measured by y is 3.99 feet. 1/10 of a second later, the distance of the mass from the ceiling is 5.84 feet, which means the mass is further from the ceiling, which means it's gone down. And 1/10 of a second after that, at 0.4 seconds, the mass of the distance of the mass from the ceiling is 7.37 feet, which means it's gone down even further. So what do we want to do? We want to know, in part A, how fast is y changing at each time? How fast is the distance of the mass from the ceiling changing at a particular instant in time? So we want to know an instantaneous rate of change, or an instantaneous velocity measured in feet per second. An instant in time is like that. However, we have to work with the data that we have, and the closest time interval we have to an instant in time from this table would be 1/10 of a second. If you look at these two values of time, which are close to 0.3 seconds, we have a time interval here that's 1/10 of a second, which is pretty close to an instant in time. But the question then becomes, if you want to know the instantaneous rate of change of the distance from the ceiling with respect to time at 0.3 seconds, should you use the time interval from 0.2 to 0.3 seconds? Or should you use the time interval from 0.3 to 0.4 seconds? It's best if you use both to find the average rate of change of the distance from the ceiling on the time interval from 0.2 to 0.3 seconds, and then find the average rate of change of the distance of the mass from the ceiling on the time interval from 0.3 to 0.4 seconds. those time intervals are both 1/10 of a second long. One comes before 0.3 seconds and one comes after 0.3 seconds. And it's best if you find the average rate of change of the distance from the ceiling on each of those two time intervals, and then take the average of those two average rates of change and use that as your approximation for the instantaneous rate of change of the distance from the ceiling with respect to time at 0.3 seconds. So that's what you see here. We calculate the average rate of change. So these are average rates of change. And this is the average of two average rates of change. And we're going to use this as our approximation for the instantaneous rate of change of the distance from the ceiling with respect to time at 0.3 seconds. So the first average rate that we look at in this column is for the time interval from 0.2 to 0.3 seconds. So we find the change in the distance from the ceiling by subtracting 5.84 minus 3.99. So there was a change of 1.85 feet. And we divide that by the change in time, 0.3 minus 0.2, or 1/10 of a second. And when we do that division, we get 18 feet per second. That was the average rate of change of the distance from the ceiling on the time interval from 0.2 to 0.3 seconds. Now we're going to find the average rate of change of the mass's distance from the ceiling on the time interval from 0.3 to 0.4 seconds. So we find the change in the distance, so 7.37 minus 5.84. So the change in the distance is 1.53 feet, and the change in time is 1/10 of a second. So we have change in distance divided by the change in time, which would give us 15.3 feet per second. So that's the average rate of change of the mass's distance from the ceiling on the time interval from 0.3 to 0.4 seconds. So when we take the average of these two average rates of change, this would give us an approximation for the instantaneous rate of change of the mass's distance from the ceiling at time is equal to 0.3 seconds. So you can see that the same thing is being done to approximate instantaneous rates of change at the other two times of 0.6 seconds and 1.0 seconds. At 0.6 seconds, you can see here we are looking at the time interval from 0.5 to 0.6 seconds first, and then from 0.6 to 0.7 seconds after. So on the first time interval from 0.5 to 0.6 seconds, we calculate the change in distance by subtracting 7.84 minus 8.00. So there's been a change in distance of negative 0.52 feet. And then we divide that by the change in time, which is 1/10 of a second, and that gives us an average rate of change on the time interval from 0.5 to 0.6 seconds of negative 5.2 feet per second. Why is this negative? Because on that time interval, the distance between the mass and the ceiling is decreasing. You can see that the distance decreased from 8 to 7.48 feet. And then we do the average rate of change of the distance with respect to time on the time interval from 0.6 to 0.7 seconds. So again, find the change in distance by subtracting 6.01 minus 7.48, which gives us a change of negative 1.47, and divide that, and that would be feet, and divide that by the change in time, which is 1/10 of a second. So the average rate of change of the distance from the ceiling with respect to time on the time interval from 0.6 to 0.7 seconds is negative 14.7 feet per second, which means the distance from the ceiling at that time is decreasing because the average rate of change is a negative value. And you can see that just by looking at these two values. At 0.6 seconds, the distance from the ceiling is 7.48 feet. At 0.7 seconds, the distance from the ceiling is 6.01 feet, which means the mass got closer to the ceiling, which means the mass is going up. So when you take the average of these two average rates of change, you get an approximation for the instantaneous rate of change of the mass's distance from the ceiling with respect to time at time is equal to 0.6 seconds. So the exact same thing is done for the third time of 1.0 seconds. We are finding the average rate of change on the time interval from 0.9 to 1.0 seconds, and then we're finding the average rate of change on the time interval from 1.0 to 1.1 seconds. Both of these are average rates of change measured in feet per second. So this is the change in distance divided by the change in time. Change in distance divided by the change in time. And then here, we're just calculating the average of these two average rates of change and using this as our approximation for the instantaneous rate of change of the distance from the ceiling with respect to time at time is equal to 1. So the second part of the problem is asking, at time is equal to 0.3, is the mass going up or down? Justify your answer. So you can do it a couple of different ways. One way is just to look at the table here, and you can see what's going on as time is moving forward. You can see that the distance from the ceiling is increasing. If the distance from the ceiling is increasing, that means the mass is getting further away from the ceiling, which means it's going down. You can also justify this by looking at our approximation for the instantaneous rate of change of the distance from the ceiling with respect to time at time is equal to 0.3 seconds. Our approximation for the instantaneous rate of change of the distance from the ceiling with respect to time at t is equal to 0.3 seconds is about 16.9 feet per second. And because this is a positive quantity, that means the distance from the ceiling is increasing at an approximate rate of 16.9 feet per second at this instant in time. And because that distance is increasing, the mass would be going down. So today we looked at calculating a rate of change by looking at a table that's given. So given a table of values that shows that y is a function of x or t, you will be able to estimate the instantaneous rate of change of y with respect to the independent variable. And we're using the same vocabulary that we've been using for the last couple of days because we are discussing the same concepts of approximating the instantaneous rate of change by using an average rate of change on a short time interval. And yesterday we looked at this in the context of a function defined by a graph, and today we look at this in the context of a function that's defined numerically by a table.